This problem is an application of Ampere's law that I hope shows you the usefulness of it. In this situation, and I'm calling this loop side A and side B, where A is equal to 20 centimeters and B is equal to 15 centimeters. Those are the dimensions. In this problem, you have a magnetic field, a uniform magnetic field that points to the right, and then it uniformly switches, it abruptly switches and points to the left. And so the question asks us to find the current encircled by this loop. So I'm going to first label all the sides. Let me use the convention I used before. So I'm starting here, 1, 2, 3, 4. Side 1, 2, 3, and 4. Why is this useful? So let's say you have a very complicated situation. Let's say you have a current running through a wire, another wire, here's a wire running the opposite direction, here's another one running out of the page, here's another one running in the opposite direction. This is not necessarily going to match this electric field, but if you wanted to just find out what is the total current of all this stuff, you could put a loop around it, use Ampere's law, and by the magnetic field, you could find the current inside there. So, for example, those clamps that measure the current through a wire by clamping around it, it's doing basically the same thing. It's measuring the electric field at all points around it, and then back calculating the current. But anyways, if we start with Ampere's law, the line integral or path integral of the magnetic field B along the path ds integrated is going to equal mu naught times the current through the path that the closed path that you laid out. Well, we can do this segment by segment, 1, 2, 3, and 4. But we notice something immediately, right? Let's look at side 1. So this is the path S, and this is the little portion of the path ds, and this is the magnetic field B. What do we notice about the two are at right angles? So the integral of B dot ds equals 0 because B is perpendicular to S, or to ds, I should say, because you're integrating, but it's a straight line, so it's going to become this. So this is the same for side 3. Same situation. The magnetic field is pointing this way, and you're integrating along this direction. Now, even though the magnetic field switches at some point, it's always perpendicular. So they equals 0. So for side 2, you have S in this direction. Why in that direction? Well, I'm just choosing to go in that direction. I mean, I could choose to go whatever direction around the loop I wanted as long as I was consistent the whole way around. Because the magnetic field is in this direction, I chose to integrate along this direction, come back, and then go back the other way along side 2. So the magnetic field is this direction. So if phi is the angle between those two vectors, then cosine of phi is 0. So B, I don't know, we're going to call it B2. What now? B ds2 is just equal to the integral along the closed path. Well, it's not a closed path because I'm doing it segment by segment. So I'm going to take the little circle out because it's not a closed path anymore. I should have done the same thing up here too. I'm being really picky about notation, but we have to be. So this is just equal to B dot ds. And you notice the magnetic field is the same at every point along here, so you can pull B out of the integral. It's just B times the integral. once I integrate this, this is just bs2, which is equal to b times a. The path distance is a. So if I go now to side 4, this side, so I'm now moving in a different direction, but I'm still moving in the same direction as the magnetic field because the magnetic field changed direction. So there's no negatives or anything to deal with. Cosine of phi, the angle between those two vectors, is still 0. So the integral of b dot ds for the cosine phi is 0, so this is just b times ds for. The magnetic field is constant everywhere on that path, so I can pull b out of the integral. So this is just the integral of s4. So that's b times s4. S4, just this path from here to here, is just BA. So then pulling it all back together, Gauss's law says that the integral around a closed path, remember that circle means around a closed path, of b dot ds, where the b is the magnetic field all along that closed path, s is the path itself, that's going to be the integral of b ds1 plus the integral of, I should put the dot product in there, b dot ds1 plus the integral of b dot ds2 plus the integral of b dot ds3 plus the integral of b dot ds4, and according to Ampere's law, that equals mu naught I through. Well, we know 1 and 3 are 0, 0. So all of these integrals together add up to the integral around the closed path. So this equals the integral of b dot ds2 and b dot ds4, which is just ba plus ba equals mu naught I enclosed, or we're looking for I. I said I enclosed, it should be I through. I'm just trying to differentiate from Gauss's law. So I through is equal to 2ba over mu naught. If you put in the numbers, that's 2 times 75 times 10 to the negative 6th Tesla times a 0.20 meters over mu naught, which is 4 pi times 10 to the negative 7th newtons per ampere squared. I through then is 24 amps.